Okay, so now to proceed, uh, we recall some definitions that we gave before just to motivate the discussion about the real numbers we've been talking about for a while. And this language we need also in section 8, which we covered last week. But just for our convenience, we're back in section 1, subsection 1 point. Well, I actually don't remember, but we will be covering least, upper bounds, and greatest lower bounds. Okay, so we'll formalize. I mean, we'll be more rigorous about what we mentioned before. So let's recall a few definitions. Remember that this means that we fully taking advantage of the order structure in R. Otherwise, the definition wouldn't make much sense. So, I mean, it would not be of use. So, definition. First one is definition 1.3.1. Tells us that a set A, so a subset of the real numbers. Now, we'll no longer make the distinction between the set that we defined as a candidate before and the actual real numbers. Now, it will be understood that these real numbers are the traditional objects that we're used to um, doing calculus on and performing operations on, the usual all real number system. So a set A, subset of the real numbers, is said to be bounded above if there exists a number B in R such that the following proposition is true. If X belongs to A, then X is less than or equal to B. Now, okay. Similarly, the set A is said to be bounded from below if there exists a lower bound L in R that is, the following proposition is true. So if X is in A, then that means that X is greater than or equal to L. Okay, well, now that we have the definition for upper and lower bound, we can talk about the least upper bound, the greatest lower bound. So definition 1.3.2. I'm sorry about that. A real number S is the least upper bound for a set A containing R if two things happen. First one is called an upper bound. It has to be, it's called a least upper bound. It has to be an upper bound. So S is an upper bound. And this is what we just defined. If B is an upper bound then B has to be bigger than S. Okay, so now we have formally defined the least upper bound and the greatest lower bound can be defined similarly. Mm. And so the notation that we introduced before the least upper bound is called the supremum, while the greatest lower bound is called the infimum. So we have the supremum and the infimum now, and we will refer to, to these numbers as either the supremum, respectively the infimum, or the least upper bound, or the greatest lower bound. I mean, we can use either one when we're referring to these numbers. Okay, so we have now every every definition in place, starting from the definition of an upper bound and lower bound. And now we have the notation for these numbers, called now the supremum and infimum. A very important thing to observe, so a very important property, so actually I'm going to make a way to a remark. The supremum is unique when it exists. Of course, I mean, we're talking about supremum means it's a number. Supremum is unique. How do we know that? Well, so suppose to see this. Suppose a set A has a supremum S1 and another one S2. Because S1 is an upper bound S1 must be greater than or equal to S2 because S2 is a supremum. So you have an upper bound, in this case S1, then S1 must be greater than or equal to S2 because of 2i. Property 2i here tells us that since S1 is an upper bound, S1 has to bound from above the supremum S2. But similarly, I mean the same way, reversing the roles of well, the same must be true. I mean the other one, so same must hold. So something completely arbitrary about picking S1 and S2. So let me rephrase that. So let me put it this way. So in the same way that we deduce this inequality, we can say that it also holds that S1, no, S2 is greater than or equal to S1. Because S2 is an upper bound, and since S1 is a supremum, then S2 must be greater than or equal to S1. These two things put together imply that they are equal. And so, therefore the supremum is unique. Okay, so we can say the same thing about the greatest lower bound. So the infimum we the infimum for a set is unique. Now, but remember that the question of existence, I mean, it's actually, this is a very strong property, the property of the supremum, the existence of a supremum or least upper bound, or the existence of greatest lower bound, or an infimum. It's a very strong one. I mean, it doesn't matter how exotic your set is. If it's bounded from above, then there is a least upper bound. That is actually pretty strong. I mean, usually you think of sets as being intervals, which is a notion you should abandon. And the quickly you do, the better your understanding of the material will be for the rest of the course. So, um, the so another remark that I wanted to make. Maybe some of you are used to thinking about subsets of real numbers as being intervals with semi-closed, closed or open intervals. Maybe in the past, um, so not maybe in the past in general, not the past for all people, but just as we use it as students. So in previous courses, it was usually the case that subsets of R corresponded to intervals for most applications and definitions, etc. So maybe many other purposes. So it's going to include those. Okay, so whenever you were given a definition of, for instance, differentiability, you had a function that was defined over an open set, but not just any open set, open interval. You were always given subsets of the real numbers that were either close or semi-close intervals, and all the theorems were stated in terms of these kinds of intervals. And as I said, in this course, will be considering much more general subsets of the real numbers. And so if we start thinking in terms of these more general subsets of R, we will realize that the property of the existence of a supremum for bounded sets is a rather remarkable one. So there's nothing ordinary or obvious about this property. Of course, if you think about say an interval AB, the supremum will be B. I mean, if it's an open interval, maybe B doesn't belong to the set, but you can actually see that B is the upper bound. Also, we'll see a bit, but if you're given a more general set described in an abstract way, then you'll see that the existence doesn't come immediately, and it's not obvious that any set would have such a supremum. And it's striking the kind of things we can do now that we have this property, and we'll be able to produce more and more sophisticated things and get a lot out of this, more sophisticated conclusions and more results that were not available to us. Okay, so one thing that I wanted to stress is that you should try to abandon this. You should try to abandon this way of thinking where when someone mentions a subset of the real numbers, it's either a closed or an open or semi-closed or semi-open interval. They're much more general sets. And this is what we'll be doing in the next, in the next video we'll see a few examples of sets that we'll be finding the supremum of and the infimum of, and hopefully this clarifies things a little bit more. Okay, so that's it for now, and see you in the next video.